Hey everyone, Active Learner here. Welcome back to another video. In today's video, we're going to discuss pre-trained network as a feature extractor, but we're going to be coding it. So I can give you a deeper understanding of how we can actually use this in the real world, right? So it's just not all mumbo jumbo concepts. So here I'm on Google Colab. You can easily make a Google Colab file on your Google Drive, and it's really useful because it already has a lot of the libraries installed for you, so you don't actually have to install TensorFlow or Keras on your own. So you can skip a lot of the setup stuff, so you can save a lot of time, and it's also very easy to share with other people, right? Okay, so first let's talk about the steps that we will be using, right? First, we'll import the necessary libraries. I've already done that, so I can save some typing time. And I'll share this file in the description, so don't worry about trying to type all of these out. And I'll also explain what each of them do, so don't worry. And then we will be pre-processing the data, and I'll explain what that looks like. And we will be loading the pre-trained weights. I'll also explain what that does. And then we will freeze all the weights in the convolutional layers, right? Because remember, the layers to freeze are adjusted depending on the similarity of the tasks to our original data set. And so let's just say our example is that we're classifying between pizza and steak, because that's what we're doing today. And ImageNet, let's say ImageNet is our original data set. ImageNet already has a lot of images of pizza and steak, so we can just freeze all the weights, right? Since the network has already been trained to extract the detailed features of our target objects, right? Okay, and then we will replace the fully connected layers of the network with our own classifier, right? I explained why we did this in our previous videos. Yeah, and then we will finally compile the network, and then we'll evaluate our performance. So yeah, let's look at our necessary libraries, right? First, we'll import image data generator. This is very useful because it allows us to do data augmentation, which we won't do in this video because of time sakes. But yeah, it also has a method called flow from directory, which allows us to read images from folders that contain images. You will use this a lot if you're working on computer vision. Okay, and then the second most important library is the second most important thing we will be importing is the VGG16 architecture. This is one of the state-of-art architectures that we will be performing transfer learning on. And this network has been trained on the ImageNet and a lot of different data sets, but primarily the ImageNet. So we'll be using this since it's very good, very powerful. And then we will also be importing MobileNet, but we aren't going to be implementing this today. This will be an exercise for you guys to try on. So you'll be needing this. And then some of the optimizers will be Atom and SGD, stochastic gradient descent. We'll be only using Atom today. You can try SGD. And then for our metrics, we're using categorical cross entropy instead of just binary cross entropy, right? Actually, you know what? Let's do binary cross entropy. Since we're predicting two classes in this case, pizza and steak, so it's a binary cross entropy. Sorry, not categorical cross entropy. And then we will input some of the layers, right? Dense, fully connected layers, right? And then flatten our output from the VGG16. I'll explain what this does. And then a dropout layer, right? So we can reduce dropout and batch normalization allows us to reduce overfitting. Okay, and then we have to import model, of course, and then we won't be using some of these stuff. I just sort of have them here. Zip file we will be using. You'll see in a minute. Okay. So yeah, let's get some coding done. Let's run this again because I changed that, right? Okay. Now, the data set we'll be using is from Daniel Burke's GitHub page. So let me just copy it really quick. And you'll get this as well. The command we'll be doing is this, right? You can find it here. This is on Google Store Cloud, so it's easier to share. And then we can use wget to actually read the file from this link, right? Okay, and then once we do that, let's see what we get, right? See, we read in the file, and you see that it is currently a zip file. So what we have to do is we have to unzip it. And how do we do that? Well, we imported something called zip file. So we can just do zip ref equals zip file dot zip file. And what is it called? Pizza steak dot zip, right? So we can do pizza steak dot zip. Okay, then we do zip ref dot extract all, right? Because we're extracting from the zip file, and then we can close it. Zip file has no zip. Oh, sorry. This should be capitalized, I believe. Yep. Okay. Now, once we have read it, let's see it. See, we have pizza, steak, right? Now it's a folder instead of just a zip file. And we have the training data and the testing data. You know, each of these, we have some pizza and steak images. If we open this, yep, there's a lot of images in there. Okay. Once we have done that, we can, let's call this getting the data. Okay, once we have done that, we can move on to the next step. Actually, before that, we have to do something else. Okay. So then we have to set up the training directory, right? Train dir, let's call it train dir. So our training directory will be this, right? If we go to train and then click on the three dots, we can copy the path, then we can just paste it here. And then same for tester, right? Test directory, we can copy the path and paste it there. Okay. And we can set up our training batches, which we can use image data generator, right? Rescale equal 1 divided 2 point. Now, you might be wondering, what does this do? Well, image data generator allows us to augment our images, right? So we're rescaling it between 1 and 255, which is normalization, right? Because the max number it can be for a pixel value is 255. And if we divide everything by 255, all the numbers will be between that value, right? It will be between 1, I believe. I think so. Yeah. So then we're normalizing our data set. Okay. Then we have to do flow from directory, right? And then in here we can put our train directory, right? Train dir, and our target size of our image is going to be 224 by 224, right? That's our target image size. That's the number of sort of the pixel. The image is 224 by 224, right? And the batch size will be 32. And you might be wondering what batch size is. Basically, it's the number of images to go through before updating the model's weights every time, every epoch, right? And an epoch is basically a forward and backward propagation, and we can set that to whatever number we want for the number of epochs. We will see later. But yeah, you might be wondering, why are we setting batch size to 32? Well, it's sort of just a general practice that many people do to set it to 32. Just like setting the random seed to 42, right? It's just a practice that people do. Okay, now we can do the same for test data. Well, in this case, we can, instead of doing test data, let's just do valid data, because I'll explain in a second, right? So why aren't we using testing data? Well, for Daniel Berg's data set, he only has training and test data. So instead of doing test data, we can just use valid data here, because we only have two things to classify, and one will be sufficient, right? So that's why valid data will be sufficient. So that's why we don't actually need test data here. And if we really want to test how accurate our model is, we can literally just upload an image and then just test if it is correct, right? Okay. Now, once we did that, the same for validation batch. And if you're wondering what validation batch is, basically you have training data, testing data, and validation data. And training data is for training the model on data, and then validation data is to see every time you train, how is the model performing on this new data, right? And then finally, testing data is after training everything, you're testing to see how our model performs after training on all the data, right? You can think of validation data as sort of a quiz and or a worksheet. Yeah, I guess training data is like learning the stuff. Validation is like a worksheet or a quiz, and testing data can be a test or a final test, something like that. Okay, now let's just run this. And you see that we have 1,500 images for our training data, right? And then only 500 for our validation data. And these two classes are pizza and steak, right? All right. Simple enough. Now let's move on. Okay. Now we are going to use our baseline model. So import the model, right? The model we're going to apply transfer learning on. So we can call it base model, because this is really just a structure, I guess. And we imported something called VGG16. Now this is a very famous model, and Keras has made this really convenient for us to import it. Instead of doing this, you can also go on to TensorHub and then just copy the URL and then paste it in. It also works like that. But this is also what you can do, which is a lot simpler. You can set the weights to ImageNet, right? These are the weights that are trained on the ImageNet. VGG16 has been trained on a lot of different image sources, right? And then in here we're going to be using ImageNet since it's more relevant to our problem, right? ImageNet has a lot of pizza and steak images, so our weights are going to be set to ImageNet. And we're going to set include top equal false, because we're going to adding our own, right? Okay, our own classification part. So we can set it to false, and input shape is going to be 224 by 224 by 3. So you might be wondering, why do we have a 3 here? Well, our image isn't only 2D, actually. It's going to be 3D, right? If you think about it, our image is 224 by 224 pixels, but it also has 3 colors, right? Red, green, and blue, RGB, right? So each one has their own layer, like red one layer, blue one layer, and then green one layer. So there's 3 here. Okay, now that we have that set, we can do for layer and base model dot layers. So we're looping through all the layers in this VGG16 model, right? All the layers. And then we're going to set layer.trainable equal false. You might be wondering, why are we setting all the layers equal to false here? Well, we do that because since our ImageNet is really similar to our problem, we can just set it to false, just basically freezing, right? Freeze all the weights in the convolutional network, right? Since ImageNet is really relevant to our problem, which is classifying between pizza and steak. So we can just set it to false, which allows us to not train it, sort of. And we can get a summary of our base model, right? Boom. Okay, so you see that there are 14 million parameters and there are 0 trainable parameters because we set trainable to false here. Okay. And yeah, if you're not familiar with how to code all of these, don't worry, because if you get enough practice in, you can basically code this on your own. Okay. Yeah. Now, once we have done that, we can add our own classifier, right? We remove the top here, we can add in our own classifier. So let's get our last layer first. Layer equal base model. Base model is VGG16 dot get layer. And oh my god, the last layer here is called block 5 pool. So we can do block 5 pool. Okay, that allows us to get the last layer, and then the last output is the output of this last layer, which is last layer dot output. Oops. Yeah, Keras has this simplified by a lot. Now, we have to flatten this output because we have to pass the output of our VGG16 network to a fully connected layer, which we have removed, right? Because we don't want to add our own classifier, so we have to remove that. Now we have to add it back. So we have to do x. We can set a variable x equal flatten upper score. We imported flatten before, so we don't actually have to. Where did we import it? So we don't have to do tf.keras.layers.flatten. That would be very difficult, right? We can just import it, and then we can do last output. This will flatten the output, right? Which we can feed through our fully connected layer, or dense layer, you could say. We can do x equal dense 64 activation equal ReLU. Right, we're using ReLU activation function to introduce non-linearity. It's the most popular one, and there's a reason for that. We can call it fully connected layer 2. Layer 2, okay. And we can pass x, okay. This will basically add it to x. And we have 64 neurons or hidden units here, so yeah. This is very random. You can put in whatever you want. You can put 128 or whatever, but I'm gonna use 64 here. And then we're going to add in batch normalization. What batch normalization allows you to do is to simplify the training process, right? It basically allows us to normalize and rescale the inputs to every layer, right? To every layer for the inputs. For example, after I pass it in through layer 1, I'm going to normalize it again for layer 2 and so on This will simplify and reduce the time required to train our model, and also offers better precision, as well as the layers are less dependent on each other. Okay, now we can add in a dropout layer to further reduce overfitting. So dropout 0.5. We pass in X again. Okay, we're basically shutting down 50% of the hidden units or neurons, right? Okay, and then we can do X equal dense to activation equals sigmoid. You might be wondering, why are we using sigmoid here and not softmax? Well, for binary classification problems, sigmoid function is preferred over sigmoid activation function is preferred over softmax because it is better for binary classification problems. And you can use softmax if you have 3 or more classes that you're trying to classify. But we're going to use sigmoid. Name can be sigmoid. This will be the layer name, by the way. Okay. And then we pass an X again. And then finally, we can declare a new model. Define a new model. Equal model. Inputs equal. The inputs will be the same. Right? Base model dot input. And then outputs, we're going to change that equal X. Okay. And now we can summarize our model. Boom. So see, now we have some trainable parameters, which is from our fully connected layer and our batch normalization layer and our sigmoid output layer, right? So this is a lot of parameters. Cool. Now we have this done. We can finally compile our model so we can, oh shoot, I forgot to, did I add the text, getting the data, import the model, configure the model. Let's call it that. Let's call it compile and fit the model. Okay. Now we can do what, since we have declared a new model up here, we can compile it, right? Compile. We can set our loss equal binary cross entropy, right? Because we are doing a binary classification, classifying between 2 classes, so it's binary cross entropy. That's our loss function. And our optimizer equal Atom, because Atom is one of the best optimizers out there. Generally, you either choose Atom or SGD, and I personally prefer Atom, but sometimes one performs better than the other, so you can test out both as an exercise. Yeah, you can do that. Okay. And then our metrics is going to be accuracy, because we aren't having bias over the other, right? Both are equally important here. Pizza and steak. I made a video on the metrics, classification metrics, so it might be better for you to watch those videos in order to understand why I'm using accuracy here, if you're confused. Okay. And then we can let's just compile this first. Now we can fit our model, right? New model dot fit, and we can pass in our train batches, right? These are our training stuff, our train data. Epochs equal to, let's run for 20 epochs, which means 20 forward and backward propagations, right? And then steps per epoch equal length of train batches. Okay. And then we can do validation data equal valid batches, and validation steps equal valid length of validation data. Okay. These are the parameters. Valid data. Oh shoot. Yeah, valid data. incorrect valid batches. Oh yeah, it's called valid batches. Sorry. So now we have passed in the parameters. We're going to run it for 20 epochs, and then the steps per epoch is going to be the length of our training batches, and the validation data is going to be our test set here, because we don't really need a test data set that big. Right, so let's run it. Oh shoot, actually let me set this to 10 epochs so it's faster. And also, are we using a GPU? We aren't. So what you can do is you can use a GPU here in order to run faster, and I forgot to do that. Okay, and here I think it's good because I can show you guys how it works. So every time we have to select GPU because we're running TensorFlow model, right? Now every time you do that, it will reset every run time, so you have to redo it. You can do run all. Okay, and it's going to take some time to run everything. Yep, we get our data. Okay. Now it should be faster because we're using a GPU. There's also a TPU, which is tensor processing unit, and that one's actually faster than GPU, but there is limited amount of it, so we're going to use GPU instead, which is also really fast, by the way. Okay, so our accuracy is around 80%, but our validation accuracy, which is on data we have never seen before, is 88%. Okay, now it's up to 93 for our validation accuracy. Let's see how high we can get it up to. 93. Okay, it might be stuck around 93, and yeah, that's pretty good. But notice how we start with an accuracy of 0.79. That's really good because that means our y-intercept for accuracy is higher already. Since we're using transfer learning, our model doesn't have to train from scratch. So, in 10 epochs, our accuracy might be better than training a model from scratch for 100 epochs. So that's the power of transfer learning here. It can allow us to have a faster training time and also higher accuracy. Okay, so it appears as that our accuracy is going to be around 94%, I presume. Now, our actual accuracy is performing a lot better than our validation accuracy, which could indicate overfitting. You can play around with this to see if you can reduce overfitting and then have higher validation accuracy. But yeah, in this video we're just gonna stick with this. So let's see, it's around 95, right? 95. That's around what we're getting. 95% correct for new data it has never seen before. So yeah, that's honestly a very good score, 95% accuracy on images. Let's see if we can see some of the images. Sorry, not sample data. Train data. You don't want to see the test data because that's bad. Yep, we can actually see it. So, this is the images we're working with here, right? We're working with this image of a steak. And let's see some of the pizza images. See, here's a pizza. Cool. So yeah, I think I can assign some exercises. We can you can try to apply pre-trained network as a feature extractor with MobileNet, which is another really well-known state-of-the-art deep learning architecture. It's really powerful, and it's also trained on the ImageNet, so you can set the weights to ImageNet as well. And yeah, compare the performance of MobileNet and VGG16 and see which one performs better. And you can also play around and see if you can get a higher validation accuracy, right? This validation accuracy is going to be really similar to our accuracy if we were to test it on testing data. So it's not necessary to have testing data here. Okay, so yeah, I can show you guys how we can use callbacks and a lot of different things later, but in this video it's sort of just a brief introduction to show you how you can actually do some of these stuff and apply it to the real world. And for the data here, you don't have to get it from Daniel Berg. You can have your own file, right? You can just have a folder of pizza steak with test and train folder within them, and you can just use image data generator to flow from directory method to actually read them. So you can do that, and you can play around with the batch size, but I don't think it matters that much. So you might be wondering, why do we actually need batch size? Well, it reduces the memory allocation, and it also allows us to train better, because that after every 32 for 32 samples we'll be updating our weights. So that's why we have batch size. Okay, and yeah, that's it for our video. It appears that it hasn't been saving, but that's okay. And yeah, that's it for our video. And if you have any more questions, you can ask them in the comments below. And yeah, sorry if my voice is a bit raspy today. I don't know what happened. Yeah, and yeah, feel free to like and subscribe. I will really appreciate it. Show your support. So yeah, that's it for our video. Thank you guys for watching, and see you guys next time.